Hello everyone. In this video, we'll learn about bin packing problem, which is a fundamental problem in combinatorial optimization. And we'll learn a simple greedy algorithm called first fit. But we'll realize that the algorithm is simple, a greedy algorithm, but the analysis is quite intricate. And in fact, we'll use something called weight functions. So let us start with the problem bin packing. In bin packing, we are given a multi-set of items, I, and there are n items, S1 up to Sn. And each item size is between 0 to 1. The same size can repeat. That's why it's multi-set. And we call a bin to be feasible if the total size of items in it is at most 1. And the goal of this problem is to partition the items into some feasible bins, and we want to minimize the number of such bins. And we'll denote the optimal by opt-I in this problem. We'll see some examples which will make it clear, but we'll realize this problem is already NP hard. So even in the offline case, when you know all the items a priori, you cannot solve the problem exactly in polynomial time for all instances. But in fact, there is also online variant where the items will appear in a sequence one by one. And once an item appears, you need to place it. And after the placement, you cannot change its placement. It should be immediate and irrevocable placement. And we'll study the first two simple greedy rules. One is next fit, other one is first fit. So let's see next fit first. It's kind of the simplest algorithm. You keep only the newest bin active, and once an item appears, you put it in that particular bin. If it can fit, it's fine. If not, then you open a new bin. And if you think a bit, it's quite easy to show it has a 2 approximation guarantee. That means NFI, which is the number of bins required to pack items in I using next fit algorithm, is at most 2 times the optimal number of bins for that instance minus 1. First fit is slightly better. Instead of closing a bin, you keep all the bins open in your algorithm, and once an item appears, you scan from the oldest to newest bin and place the item in the first feasible bin. And if it does not fit in any of the previous bins, then only open a new bin. So both the algorithms are quite simple, and it will be easier if we understand by an example. So think of there are 6 items which appears here, and we'll see how next fit and first fit packs them. So first 0.3 comes, and you open a new bin and put 0.3 in both cases. Next 0.8 comes. In next fit, you try to put in the first bin, you're not able to put, so you close this bin and you open a next bin and you put 0.8 there, and same thing will happen in first fit as well. Next item is 0.2. Now you have already closed the first bin in next fit, so you'll try to put the 0.2 in the second bin, which is the present open bin. It is there, so you place it here. But instead of doing that in first fit, what you do is you still see among the 2 open bins now, 0.2 can be placed in the first bin because there is enough space. The total space is 1, and only 0.3 was placed. So we can place it, and we'll place in the first bin. So there already first bin is differing from first fit is differing from next fit algorithm. Next 0.3 comes, and now we cannot pack it in the second bin in next fit, so we open a third bin. But again, in this case, in first fit, we can place it in the first bin, so we are fine. And then 0.8 comes, we place it in the next bins, and 0.3 comes, we place it in the next bins because it is not fitting anywhere. So spend a minute understanding the algorithm. Both algorithms are quite simple. Probably the first algorithm that will come across your mind if you're trying to solve bin packing problem. Now, to do the analysis, we need to understand the properties of these algorithms. And one simple property of next fit is this, that if I look at a bin B, let's say this is a bin B, and some B prime, which is a consecutive bin, and let's say first item which was placed in B prime is X, then the reason X was placed in B prime, it opened a new bin, is because X was, we were not able to pack X in the previous bin B. That means the load of B, which is total size of items which are inside B, plus X, it should exceed 1. Otherwise, we could have placed X inside bin B. That's the property of next fit. And in fact, using this property itself, you can show a guarantee of two approximation. Intuitively, if I to take any two consecutive bins, their total load is crossing 1. Now, first fit has extra properties and which are helpful to beat the factor of 2. We'll get actually 1.7 asymptotic approximation guarantee. So in this case, it's not only about consecutive bins, but if I take any bin B and any bin C, which was opened later, so let's say this is one bin B and this another bin, let's say any bin later C. And then if I look at any item X in C, when X arrived, we always try to put in the previous bins. So we were not able to put in bin B, that's why we put it in bin C. That means for every item in C, if we are not able to pack them in bin B, X plus load of B should be more than 1. Okay, this is the inequality. And we'll see this inequality will drive the entire analysis of first fit. The simple property is actually really powerful. Now let us spend some more time understanding this algorithm first fit. First, the ordering or the arrival order matters. And same item set, if they have different arrival order, yeah, the number of bins returned by first fit can be quite different. So think of this example where there are 6 items, same item set, but the orderings are different. In the first order, first 0.3 comes, then 0.8, then 0.2, then 0.3, then 0.8, and 0.3. We open 4 number of bins. In the second case, first 0.8 comes, then 0.8, then 0.3, then 0.3, then 0.2, and then 0.2. Then 0.3 and then 0.2. In this case, we pack 3 bins. So the reason it is different in the first example, we already put 0.3 in the first bin, and then we had to place 0.8 and 0.8 in the next 2 bins. But then once the item 0.2 appears, we place it with this one, which was the first bin, whereas in this case, we place in a different first bin. And that gives us a better packing and we get less number of bins. So first fit is an algorithm for the sequence, not only for the multi-set. So it depends on what is the ordering. And in fact, one can show that for any input, there exists a sequence for which first fit will return the optimal offline packing. But as already bin packing is NP hard, for finding this optimal permutation is also NP hard. Now there are some interesting properties of first fit. We'll see one of them is first fit is non-monotone. That means intuitively we believe that if we have some set of items and I increase the size of the items, then op should go up, and that is true. And similarly, if I decrease the item size, op should go down. But similar properties are not true for first fit. So let's say this is one sequence and this is a second sequence. In this sequence, actually, we have a smaller item. Instead of 7 by 10, we have 3 by 10 or 6 by 20, which is a slightly smaller item. And the remaining items are same. Now, if we run first fit, in the first example, it will be packed in 3 bins. The second example, you will need 4 bins. The reason being, the 3 by 10 here the 7 by 10 is ensuring some other future item comes here and which is blocking packing of some other items, packing of 3 by 5 items which comes later. But in this case, basically packing of the 7 by 10 is good. It's a local improvement, but it creates a problem to pack the later 3 by 5 items, which needs more bin. So if you spend a minute, pause it, you'll understand that even if we shrink the size, the opt can go up. Now we'll see 4 structural consequences of first fit, and these properties will be useful in the analysis. So first property is the blocking property, which I already mentioned earlier, that for any item X which comes in a later bin C, as X was we are not able to place X in earlier bin B, so X plus total load of bin B is more than 1. And that will lead to these other 3 properties. So first of all, very light bins which have load at most half. The claim is only one such bin can exist. For contradiction, assume that there are 2 bins which have load less than half. So some bin B and some bin C, and both have load less than half. But then that means the items which are there in bin C their size is less than half, so they can anyway be placed in bin B, will not open bin C, which is a contradiction. So at most one bin can have load at most half. And from that, we can conclude that if I look at a bin which is singleton, it only contains one item. Already we know only one bin can have load less than half. So only one singleton bin can contain an item which has size less than half. Because if there are two singleton bins which have item size less than half, again, you can combine them together and total size will be less than 1. And another interesting property is this multi-item bin property. If there are bins, if we consider those bins which have more than 2 items or at least 2 items, their load is more than equal to is at least 2 by 3 except one bin. For example, if I look at one particular bin which has, let's say, load less than 2/3, which is a multi-item bin, at least 2 items are there. Now, if I look at any other multi-item bin which has 2 items, let's say X and Y, we know that we tried to put X here and Y here and we were not able to do. Now, the load of this bin is less than or equal to 2/3. That means both X is strictly more than 1/3 and Y is strictly more than 1/3. That's why we were not able to place it. That means total load of X and Y is at least 2/3. So at most one bin will have load less than or equal to 2/3. And these 4 properties we'll use later in the analysis. And in the analysis, we'll use something called weight function. And it's a very powerful technique in bin packing and other related problems. So what is a weight function? It's kind of a price you are putting on an item. Now, if you look at bin packing, there can be, we don't know opt because it's NP hard, but we can place some lower bounds on opt. So one lower bound on opt could be size of the items, the total size of all items. I need at least that many number of bins to pack all items. And but that's not only that's not sufficient. Think of the case when all items are size half plus epsilon. Then each item will need a separate bin, singleton bin. So even if the total size, let's say n by 2 plus epsilon, roughly, you still need n number of bins. So size and opt can be even almost factored 2 apart. So for this kind of items, we want to place some more weight so that we can charge this item in opt in some other way. So this weight function is kind of a way to put some price on the item such that we can charge the algorithm side and the opt side and say, okay, they're not too far apart. Now in weight function, we have a function W which takes the size of the item, which is between 0 to 1, and puts a non-negative quantity on that. And we can say that the total weight of a subset of items is just sum of the weights of individual items. Now we have 2 sides. One is algorithm side, where we are saying that, okay, each bin in the algorithm has some weight. So think of total weight is L times AI minus beta, where AI is the number of bins returned by the algorithm on input I. L is some constant and beta is some constant. So algorithm side has some weight. This is just showing that if I look at Wi by AI, that is the average weight per bin, that's kind of roughly L, ignoring the beta, the constant. And in most cases, we'll actually take L equal to 1. So roughly, we want to show that most bins, except maybe a constant number of bins in your algorithm, has weight at least 1. In the benchmark side, on the other hand, we'll show that none of the bins, even in the optimal solution, will have large weight. So they're upper bounded by some weight U. So the analysis kind of uses the fact that, okay, what structural event guarantees the payment from algorithm side, and how small can we make the universal capacity? So there is a dichotomy. If I make weights large, then algorithm side is good, but benchmark side will lose out. On the other hand, if we make weights to be smaller, then algorithm side will lose out. So there is a tension between these two aspects, and we try to balance it by choosing a good weight functions. So this is basically comparing this weight of items. So already the condition is showing that Wi is more than this. But also from this condition, we know if there are opt number of bins and each bin has weight U, so then if you look at all items and I kind of break them, partition them into the optimal packing, I know Wi is less than or equal to U opt. So this is kind of the same currency Wi is being used to compare AI and opt. This is a more formal proof. Suppose that for every instance I, we can choose a weight function W and some constants L, U, and beta, such that Wi is more than L times AI minus beta, except some small constant number of bins. Other bins in the algorithm on average has good weight. And then we show for every feasible bin, it is upper bounded by U, then we get U by L approximation guarantee, ignoring the constant. So we are in the asymptotic setting, so we'll ignore the constant beta, and because when in the asymptotic setting, opt is very large, so you can ignore beta compared to opt. So we kind of get the asymptotic approximation ratio to be U by L. And this is the proof which I already discussed. Okay. So now let's try to understand what kind of instances are bad for first fit. So as you see that if the items are half plus epsilon, that's already bad because I mean all the items half plus epsilon, then we need to open separate bins. So in first fit, if at the end this kind of items appear, that's lossy because we cannot place two of them together. But maybe in the opt, they were placed with other items. And from that, you can, if you think a bit, you will come up with this kind of examples. So there are n by 3 items which are of size 1/6 minus 2 delta, n by 3 of size 1/3 plus delta, and n by 3 of size half plus delta. Delta is very small. So in this case, what will happen in first fit, the first n by 3 item appears and 6 items can be packed in one bin. So think of these items as delta is such that you can pack 6 but not 7. So delta is very small. Then you can pack 2 medium items per bin. Any 2 medium items will fit but not 3. And then at the end, this large items half plus delta comes, you can pack them and you can pack them in n by 3 number of bins. So total, it will produce 5n by 9 number of bins. Whereas in opt, you can mix them. And in fact, you can show, you can just pack 1 half plus delta, 1/3 plus delta, and 1/6 minus 2 delta 1 item together. Total size is 1. So you can pack in n by 3 number of bins in opt. So the ratio between first fit and opt is 5 by 3. This is already showing that there are examples for which you cannot beat 5 by 3 using first fit algorithm. And there is a more intricate analysis. So for example, if items were 1/6 plus epsilon, 1/3 plus epsilon, and half plus epsilon, then again, in this case, the number of bins you will need to pack them will become, instead of n by 18, n by 15, because if it is 1/6 plus epsilon, then you can pack 5 of them, but not 6 of them. So that will give you 17 by 17 n by 30. But the issue is then these 3 items also cannot be packed together. Half plus epsilon, 1/3 plus epsilon plus 1/6 plus epsilon is already more than 1. But then one can do a finer analysis and perturb the values near 1/6 carefully and then construct an instance for which actually we can reach a lower bound of 17 by 10. So you cannot beat 17 by 10 for first fit using first fit, you cannot beat 17 by 10 ratio. And we'll now see the tight guarantee. Like actually, it is 7 by 10, 17 by 10 ratio. You can prove theoretically that first fit can achieve. Now, let me briefly mention that ordering of the items changes guarantees. So the first fit algorithm was devised by people in 1970s, like Turing-out winner J. Fullman, and also David Johnson, Kaufman, Gary, and a lot of other people. They studied this algorithm in 70s, the late 70s, and they showed that there is a 17 by 10 asymptotic guarantee, which also we'll see in this proof. But then there was a sequence of work which finally led to the proper understanding that actually earlier the bound were at 1.7 opt plus some constant, but then the tight guarantee was shown by Dosa and Sgull in 2013, where they showed it is actually 1.7 opt floor and this is tight. Now, if we are allowed to sort the items, if we sort them in increasing order, then one can show it increases slightly, the performance is slightly better it reaches some quantity called T infinity, which is roughly 1.69103. In fact, one can show that if I do this increasing ordering, then first fit and next fit are similar in power. So first fit increasing and next fit increasing both achieve this 1.69103. But if I use first fit decreasing, then it is much better. In fact, then we can achieve, so next fit will, again, if we decrease the item according to the size, next fit will achieve the same bound 1.69103. But for first fit, you'll improve a lot. You'll get 11 by 9, which is like 1.22 asymptotic approximation guarantee. And again, a sequence of work showed the tied case, which is plus 6 by 9. But earlier from 70, that was plus 4, then plus 3, and the sequence of work finally led to the complete understanding of bounds. Now, there is some further improvement. There is some algorithm called modified first fit or MFFT, which is a more refined offline rule where you deal the large, medium, and small items in a better way, and you can get a guarantee like 1.18. And this is kind of the best practical algorithm that we have for bin packing, which runs quite fast in practice. So this ends the basic discussion about first fit. And the next part, we'll do the analysis of first fit and reach the tight asymptotic approximation guarantee.